Let's now look at one of the trickiest kind of questions, which is buffers. A buffer is a solution which resists or prevents the change of pH. Even when small amounts of acid or alkali, acid or base that is, are added, then a buffer will prevent the pH changing to some degree. Let's have a look at the kind of question that we have. It starts off in a usual fashion, but then it changes, and I'll explain the changes. When you see the word buffer, because you've got a strong base reacting with a weak acid, then the rules change. But it starts off normally 10 centimeter cubed, which is 0.01. I've got a volume of 0.1 concentration potassium hydroxide. Concentration 0.1 equals moles divided by 0.01. I'll multiply the two together to get number of moles of potassium hydroxide. I do the same for the ethanoic acid. 0.41 multiplied by this in decimeter cubed is 0.025. Multiply the two numbers together to get number of moles of ethanoic acid. Then I do the same again. I look at them. Now I've not got a diprotic acid like sulfuric acid. It's not a superacid. So 1 mole of potassium hydroxide reacts with 1 mole of ethanoic acid. So 1 mole of this reacts with 1 mole of this, but I've not got this similar amounts. So I must have something left over. What have I got most of? What have I got most of and is going to end up in excess or left over? Well, 0.01025 is larger than 0.001, so I've got ethanoic acid in excess. I subtract the two numbers away from each other, because number of moles of potassium hydroxide 0.001 is going to react with 0.001 of ethanoic acid, but I've got more than I need, so I subtract the two to work out how much I've got in excess, how much ethanoic acid I've got left over, because I've got more than I need. I know for a weak acid that my acid dissociation constant is this. We've done this several times before, and I've been given it earlier on in the question. It equals 0.000174. Okay, this is where it changes. Now, I cancel a square brackets on the top and a square brackets on the bottom, and those two are the ones that are cancelled. This square brackets here and this square brackets here to leave this. My H plus concentration stays the same. I'm not cancelling that. I'm just cancelling this square brackets on my CH3COO minus and my square brackets on my CH3COOH from the top and the bottom. And it changes concentration into moles. The reason I can do that, you don't really need to know, but the reason that I can do that is because to turn moles into concentration, I've been dividing by the same volume, top and bottom, and so it cancels each other out. But just think of it as cancelling the square brackets on the top and the square brackets on the bottom to leave the only thing with square brackets is the H plus. Now I can look at these two. Have I got the number of moles of ethanoic acid in the solution? Yes, that's the number of moles of ethanoic acid that are left over after the potassium hydroxide and ethanoic acid have neutralized each other, reacted with each other to make a salt and water. So it's this amount that I've got left over of my ethanoic acid, and that's this one here. So 0.000174 multiplied by 0.00925 equals, those two multiplied together equals moles of CH3COO minus multiplied by H plus. Okay. I still can't work out H plus concentration, which I'll need to work out pH, because I don't know this one. Okay. And this is the next little trick. The number of moles of this CH3COO minus, which is an ethanoate ion, is the same as the number of moles of your base. So the number of moles of ethanoate ion is the same as the number of moles of your base. So this one here is 0.001. Moles of your base, 0.001. I take this down to the bottom, so 0.000174 multiplied by 0.00925 divided by 0.001 equals my H plus concentration. That'll equal 0.000161 minus log to the base 10 of it. You've got the pH of the buffer solution. Is that correct? pH 3.79 if I've got ethanoic acid in excess. Yes, that looks like the pH of a weak acid. Let's try it again then. Methanoic acid. It says I've got a buffer solution. I have got a concentration of methanoic acid. Here's my concentration of methanoic acid, and I've got a concentration of something called sodium methanoate. So this is a slightly different question, and I've got Ka. So why I've been given Ka for methanoic acid? So Ka equals the concentration of CH3COO minus multiplied by the concentration of H plus divided by the concentration of methanoic acid, and equals 0.00178. Okay, let's go through my logical steps. I cancel the concentration of this one and the concentration of this one by cancelling the square brackets top and bottom. So now 0.00178 equals the moles of this CHOO minus multiplied by H plus concentration divided by the moles of CH3COOH, my methanoic acid. Have I got any values so far? Well, in actual fact, I've been given them, so it's slightly easier than my last question where I needed to work them out. I've actually been given these two values here, the number of moles. So the number of moles of CHOO minus, which is sodium methanoate, that's what it is 1.84 times 10 to the minus 2, 0.0184, and the number of moles of methanoic acid I've been given is here, 2.35 times 10 to the minus 2. I put them in, I rearrange the equation, so 0.00178 equals multiplied by 0.0235, because this is on the bottom on this side, ends up on the top on the other side, divided by 0.0184, it's on the top on this side, so ends up on the bottom on the other side. It should give you a value of 0.000227 minus log to the base 10 of it equals 3.64. Okay. Now the last and final part, which is tricky. I have 5 centimetre cubed of 0.1 hydrochloric acid, and it's added to the buffer. Calculate the new pH of the solution. I know if it's a buffer it shouldn't change very much. It resists. It doesn't completely stop changing in pH, but it does stop it to some degree. So I know that this value of a buffer solution is not going to change very much when I add hydrochloric acid. Hydrochloric acid is an acid, and so it's going to bring it down slightly, but not very much. So I'm looking for a value a little bit lower than this. Okay, what do I do first of all? Well, I've got 5 centimetre cubed. I've got a volume, which is 0.005 decimetre cubed, of 0.1 hydrochloric acid. I've got a concentration. So 0.1, the concentration, equals number of moles divided by 0.005 decimetre cubed. If I multiply these two together, I'll find out the number of moles of hydrochloric acid. That's got to be the first step. So number of moles of hydrochloric acid added, these two multiplied together, 0.005 multiplied by 0.1 is 0.0005. Okay. Now, what does that do? Well, it puts an extra 0.0005 moles of acid into the solution. Okay. So I get an extra number of moles of H plus in the solution. So my number of moles of methanoic acid has just gone up by 0.0005. When it reacts, when the acid reacts, then it reacts with this, CHOO minus. It reacts with this, and that goes down by the same amount. It was 0.0184, and now it goes down by 0.0005. So when I add an acid, it brings the acid number of moles up, this value up by the number of moles, and it takes this value down by the same amount. So I see what I had before, and I change these two values. This value, my acid, goes up by however many moles it is, and the other one goes down by however many moles it is, and I recalculate this calculation here based on that, and my H plus concentration changes and my pH changes. So I recalculate H plus concentration and I recalculate pH, which is minus log to the base 10 of it. 3.62. Well, I've just added some acid, so it's going to bring it down from 3.64, but the buffer resists, tries to prevent the pH changing very much at all, and it has. It's gone down slightly, but not very much at all.